Okay, so the purpose of this video is to show everything there is to know about the modulo operation, which is this operator. Now, I'm gonna start with the basics, but the main purpose is to cover advanced topics. If you want, you can skip the beginning and go straight to the advanced stuff, but I'm gonna try to cover the mathematics of this, so the foundation is gonna help for the advanced concepts, hopefully. So let's get started. The model operator is a binary operation between two numbers, A and B. So let's look at some examples. 12 modulo 12 gives us 0. 13 modulo 12 gives us 1. Why? Because if you divide 13 by 12, 12 goes into 13 once and the remainder is 1. And we actually use this in everyday life with the 12-hour clock because 13 hours is the same as 1 p.m. 23 hours is the same as 11 p.m. and 24 more 12 goes into 24 twice and the remainder is 0. Another way to see the same is like in this wheel where we have 12 numbers from 0 to 11 and after that it just wraps. 12 is 0, 13 is 1 and so on, and then 24 is 0, 25 is 1 and so on. It just keeps cycling. So that's why modular arithmetic is also called clock arithmetic. Now, mod 12 is something we are familiar with, but the same can be used for any number. So this is mod 8, again, 8 numbers, and then every multiple of 8 is gonna be 0. The remainder is 0, 24, 32, and so on. If we go to mod 4, it's 4 is gonna be 0, 8 is gonna be 0, and so on. And for example, this can be used for, this also used for to check if a number is even or odd. Even, odd, even, odd, even, odd, and so on. This is mod 2. So that's basically it. That's the modulo operator. That's what most programmers know, and that's really what most programmers need to know. But in order to cover the advanced stuff, I think it's useful to see the mathematics. Now, the modulo operator, as I said, it operates on two numbers. The second number is called the modulus. So 13 mod 12, 12 is the modulus, and the result is the remainder, like 1. But this operator is a computational operation, not mathematic. The mathematics is covered in modular arithmetic, and these things are not the same. They are related, but not exactly the same, and we'll see why in a moment. So in mathematics, these equivalences are covered in modular arithmetic, and it's different. Instead of using an operator, we say that two numbers are this means that they are equivalent in a certain modulus. So let's take a look at this example that we saw before. 13 mod 12 equals 1. That's the computation operator. In mathematics, we say that the 13 is equivalent to 1 in mod 12. Why? Because if we look at this wheel, 13 is here. So let's add more numbers. So 13 and 1 are equivalent. 14 and 2 are also equivalent. 15 and 3 and so on. And we can add more. 25 is equivalent to 1 also. So all these three numbers and so on are equivalent. That's what this means. But really, what we are trying to say is that two numbers a and b are equivalent if in programming the remainder is the same. So 13 mod 12 the remaining is 1, 25 mod 12 the remainder is 1. So 13 and 25 are equivalent in mod 12, and that means that they are in the same spoke of this wheel. Okay? And this symbol is actually called modular congruence. So 13 is equivalent to 25, or another way to say it is that 13 is congruent to 25. The same thing. For all intent purposes, they are equivalent in this arithmetic mod 12. We can check in Wolfram Alpha that that's indeed the case. 13 congruent 25 mod 12 equals true. So these two numbers are equivalent or congruent. More formally, this expression means these are the integers, but this thing is the ring of integers modulo 4. And this is a set that contains 4 elements. If we look at mod, this is mod 4, we see that there's 4 blocks, 0, 1, 2, and 3. Yeah, 0, 1, 2, and 3. Now, each one of these is not a single number, is in fact a set of numbers. And this is all the integers that are congruent to 0 in modulo 4. Like 0, 4, 8. All these are equivalent. And we can see 0, 4, 8, all those are equivalent. And then 1, 5, and 9 equivalent. 2, 6, 10, and so on. So this is more formally. The ring of integers modulo 4 is a set of 4 elements, and each element is itself a set which contains all the integers that are congruent to 0, to 1, to 2, and to 3. Now, that's basically it. But there's a couple of things that are useful when we see the mathematics. For example, 3 plus 1 is 4, but 4 is not in the set. 4 is congruent to 0. So 3 plus 1 is 0, as we can see here. 3, and then we add 1, it's 0. But the same applies for any number which is congruent to 3 and 1. Let's add more numbers here. For example, 3 and 1 is 4, but 5 and 7 is 12, and 12 is here. And any two numbers in here plus any number here is gonna give us a number here. 9 and 11 is 20, and 20 is of course here. So that's one thing that the mathematics help us to see. There's two other important things here. First, we could choose any number to represent these equivalence classes. So this one could be 4, this one could be 9, and so on. So why these numbers? Well, it's just convention that we pick a number that is representative of the equivalence class using the smallest non-negative integer. So in this case it's 0 because this one is negative. This one is not the smallest, this one is the smallest. So it's 0, 1, 2, and 3. So that's one thing. The other thing is that we can see negatives here, and this will be useful in a moment. Okay, so this is where things start to get interesting. This is the main part of the video. What we want to see is how the negatives work in modulo. So if we go back to the math, we can see, for example, that -3 and -7 are congruent to 1 under modulo 4. So if we go back to this wheel and modulo 4, so 4 minus 1 is 3, so 0 minus 1 has to be 3, which is what we see here. Minus 1. So -1 is congruent to 3. We can add the negatives here, and we can see -4, -3, -1, 2, and 1. Okay? Now, let's go to modulo 12. What we can do, we can think like this way. When it's -2, it's 2 hours before 12. So if it's 2 hours before 12, what is the hour? 10. That's what -2 modulo 12 gives us. And we actually use this in everyday life. For example, this is modulo 60, like 60 minutes. And if there's a meeting at 3, there's 15 minutes left. What is the time? 2:45. We can check that's indeed the case. Negative 15 mod 60 45. So that's the basics of how negative numbers work in modulo. The positives are like a positive count, like this is 6 hours after 12, and the negatives are like negative countdown, 5, 4, 3, 2, 1, which is the same as normal negatives, except they wrap. So it's like a cyclic countdown. Now, here it's negative 2 gives us 10. But what if we want to do it the other way? If we have 10 and we want negative 2. Well, for these simple operations, we don't even need modulo, because negative 2 plus 12 is 10, and 10 minus 12 is negative 2. So in those cases, it's easy to do the operation. But what if the number is bigger? Like 34. So we can see from here one way we can do this. So if it's 34 mod 12, let me clear this, that's 10, then 10 minus 12 is going to give us negative 2. So if the hour is 34, it's 2 hours before the next cycle. So 36 mod 12 is going to be 0. Right? 1, 2. So that's one way of doing it. But there's another way. If we change the sign of the modulus, so it's modulo negative 12, this wheel is kind of mirrored. So this is negative 2 gives us 10, and then this is 10 gives us negative 2. So it's the same thing, but the other way around. So you can say 10 mod negative 12, that gives us negative 2. So 34 mod negative 12 gives us negative 2. So this is like a shortcut. If we see what the operation does, is the same thing like the countdown, but this is straightforward. So 45 mod negative 12 is going to give us negative 3. 3, 2, 1, 0. Okay? So that's negative on the numerator, and that's negative on the modulus. Okay? But it turns out there's an identity. We can just change the symbol, the sign, and it's the same thing. It's hard to see, but 10 mod negative 12 is the same thing as 10 mod 12, except not negative. And let's change, let's reset. That identity is hard to see, but we can see that, so here's 0, 10 is 2 before 0, so the distance is -2, and in the positive distance, this is like a mirror, 2 and -10. We can check that this is true for more numbers. So 10 and 22, -10, -22. 8 and 20, -8 and -20. So the distance from 0 is kind of mirrored. -4, +4. So that's why the identity holds true. And in fact, I have the formula here in Wolfram alpha, x mod -m and -x mod m. The result is exactly the same. So these two are equivalent. This floor is gonna be important later on, but for now, that's basically it. That's all there is to know about negative numbers in modulo. Just you can just ignore the negative modulus and then just use negative on the numerator, and that's gonna give you the same thing. But it turns out that everything that I said is partly true, because -10 mod 12 gives us 2 in Python, but in JavaScript it's -10. So it's not the same thing. So it turns out that it depends on the programming language, because some programming languages use the truncation method and others use the floor method. That's why the results are different. Now, we know that -10 and 2 are congruent from the mathematics. Let's -2 and 10, right? No, -10 and 2. These two are congruent, so they should be considered basically the same number. But this is not, in my opinion, is not useful in programming, because in programming I want this. I want only 12 numbers if we are operating it mod 12. Now, the reason for that is that let's work in JavaScript. The quotient is calculated with truncation like this. So it's 0, but if we use floor, it's -1. So there's always an offset of 1 between the two methods, and then the remainder is going to be so if this is the quotient, the remainder is going to be x, which is -10 in this case, minus the modulo 12 times the quotient. So it's the remainder is 10 in JavaScript. But if we use floor, it's 2. That's in Python. So we could use our own formula using the floor, but turns out there's a way to convert one one to the other, which is more efficient. So JavaScript is going to return a negative number, but it's a negative number that is close to 0. So we know that if we add 12, what the modulus, the result is congruent as well. So that converts it to the Python version, except there's one corner case. If it's exactly 12, then we get 12. So for that case, we just mod the whole thing again. That's the formula. So let's create a formula. Mod floor xm, that's gonna be x mod m plus m mod m. That's it. So now negative 10 mod 12 gives us 2, like in Python, and mod 10 negative 10 mod negative 12 gives us negative 2. So that's it. This is the formula. If your programming language is using the truncation method, which I think it's less useful, then you can use this formula to convert one to the other. And actually, I have here a list. You can see most programming languages use the truncated method. So if your programming language is one of those, this is the formula that you can use to convert from the truncated result to the floored result. So that's it. That's everything there is to know about the modulo operator. I have covered the basics. I have covered the modular arithmetic, the mathematics side of it, how it works with negative numbers, and the difference in implementation in different programming languages. So hopefully you liked the video, and if you did, let me know. Click the thumbs up button, and yeah, that's it. Cheers.